Good morning to all of you. In previous sessions, we were discussing the properties of the Z transform, where we are seeing linearity property, time shifting, scaling in the Z domain, time reversal, differentiation in the Z domain, right? And in previous session, we discussed the convolution of two sequences, right? So in today's session, we'll be discussing another property, that is correlation of two sequences. Okay, and we'll try to identify the correlation sequence by using this correlation property of the Z transform. So in case of correlation of two sequences property, if we have two discrete time sequences, that is x1 of n and x2 of n, so these are the two discrete time sequences with their Z transform, capital X1 of Z and X2 of Z respectively. Okay, so then the correlation of these two sequences, that is X1 of n and X2 of n, we know that the correlation of X of n and Y of n, we have seen the formula for cross correlation of these two sequences. So this can be given as Rxy of L, which is equals to summation n is equals to minus infinity to infinity x of n into y of n minus L. Okay, so this is the formula for cross correlation, right? So here in place of x of n and y of n, we are taking x1 of n and x2 of n. Okay, so the cross correlation of these two sequences, x1 of n and x2 of n, will be denoted as Rx1 x2 of L. Okay, and the formula for that will be summation, again it will be n is equals to minus infinity to infinity, right, x of n into, that is x1 of n into x2 of n minus L. Okay, so it is in time domain. Okay, so in Z domain, this cross correlation will be simply the multiplication of x1 of Z multiplied by x2 of Z inverse. Okay, in previous session we have seen the convolution of x1 of n and x2 of n is the multiplication of their respective Z transform in Z domain, that is x1 of Z multiplied by x2 of Z. In case of correlation, the correlation of two sequences in Z domain will be the multiplication of x1 of Z, that is the Z transform of first sequence, and the this is nothing but as per the time reversal property. Okay, that is x2 of Z inverse. Okay, so this multiplication in Z domain indicates the correlation of these two sequences. Okay, that is x1 of n and x2 of n. So we can indicate it here in terms of capital R x1 x2 of Z. Okay, so this is in time domain and this is in Z domain, right? So this is the correlation property of Z transform. Okay, so this is one of the Z transform property, which is nothing but correlation of two sequences. Okay, so the ROC of this Rx1 x2 of Z, that is the ROC of Rx1 x2 of Z, is at least the intersection of ROCs of x1 of z and x2 of z inverse. So we'll try to prove this property again here. So in proof we can write here we know that the convolution, okay, convolution, if I want to indicate the convolution x1 of n with convolution of x2 of n, okay, so the convolution formula will be equals to minus infinity to infinity, so k is equals to minus infinity to infinity x of k into x1 of k into x2 of n minus k. Okay, so this is the formula for convolution, right? So just for example, if I'm taking the variable here as L, okay, so this x1 of L convert with x2 of L, okay, and in place of this variable that is nothing but k, if I am taking this value that is nothing but, in place of k, if I'm taking n, okay, n is equals to minus infinity to infinity, right? So it will be x1 of n multiplied by x2 of L minus n, right? This is as per convolution formula. So if I am in this formula, this convolution formula, say this is convolution formula, right? x1 of n convolved with x2 of n, as per convolution formula we can write k is equals to minus infinity to x1 of k into x2 of n minus k. So in place of n, if I am taking L variable, and in place of k, if I am taking n variable, right? So again, this is nothing but the convolution formula. Okay, so I'll just rewrite here that convolution, that is x1 of L convolved with x2 of L. So here I am taking the summation variable as n is equals to minus infinity to infinity. So x1 of n into x2 of what, L minus n will be there, right? So if now I am replacing this x2 of L with x2 of minus L, okay, that means instead of convolving x1 of L with x2 of L, if I am convolving x1 of L with x2 of minus L, okay, so what will be changes here? So it will be simply summation n is equals to minus infinity to infinity, right? x1 of n will be as it is there, right? Multiplied by x2 of what, here this will be, I'm replacing this complete with minus sign, okay, so it will be simply n minus l, correct? So this thing, that is summation n is equals to minus infinity to infinity x1 of n multiplied by x2 of n minus l, is nothing but the cross correlation, that is r x1 x2 of l, right? Correct. So this is the formula for what, correlation, cross correlation of x1 and x2. So this is nothing but r x1 x2 of l, right? So here we can say that, so this star indicates the convolution operator. Here we can say that this r x1 x2 of l is equals to the convolution of x1 of l and x2 of minus l, right? As per the convolution formula, we will get this n is equals to minus infinity to infinity x1 of n into x2 of n minus l. So this is nothing but the cross correlation, okay, represented in terms of the convolution of x1 of l and x2 of minus l, correct? So by using the convolution property, okay, we have seen convolution property in previous session. By using the convolution property and time reversal property, property of Z transform, what we will get as per this convolution property, this time domain cross correlation can be represented as r x1 x2 of z in Z domain, and it will be, as per convolution property, it will be simply the multiplication of these Z transform, okay, that is Z transform of x1 and x2, okay. So these are x1 x2 of z is nothing but the multiplication of Z transform of x1 of l multiplied with Z transform of x2 of minus l, okay. So the Z transform of x1 of l can be simply represented as x1 of z, right? And the Z transform of x2 of minus l, as per the time reversal property, it can be represented as x2 of z inverse, right? So this will be nothing but the cross correlation of x1 and x2 signal, that is x2 x1 of n and x2 of n, okay. So this is the required cross correlation in Z domain, that is nothing but the multiplication of x1 of z and x2 of z inverse. So here this x2 of z inverse were written as per this time reversal property of Z transform, because we know that if x1 x of n has the Z transform x of z, then this x of minus n as the Z transform x of z inverse, okay, as per the time reversal property, right? So this is nothing but the correlation property of Z transform, where we have been provided with two signals, that is x1 of n and x2 of n, with their respective Z transform, that is x1 capital X1 of z and x2 of z respectively. So the correlation of x1 of n and x2 of n in Z domain will be the multiplication of x1 of z and x2 of z inverse, right? So we'll try to solve one problem where we'll determine the autocorrelation sequence of the signal. Okay, so we have solved it in previous session by using formula. Here origin is not given, so you can consider this first sample as the origin. When the origin is not provided, so you can consider first sample as the origin sample, right? So we know the autocorrelation formula, that is Rxx of L is equals to summation n is equals to minus infinity to infinity x of n into x of n minus L, okay. So this is the formula for autocorrelation, okay. So here we want to determine the autocorrelation by using the correlation property of the Z transform, okay. So here we can write down as per the auto as per correlation property of say transform, the autocorrelation sequence for signal x of n is given as, so we can represent it as, it will be in z domain. Okay, rxx of z is equals to capital X of z, right? Because there will be only one signal, that is x of n. So as per correlation property, it will be x of z multiplied by x of z inverse, right? So rxx of z is equals to x of z multiplied by x of z inverse, right? So to identify this autocorrelation sequence, basically here what we're representing, so we're simply identifying this autocorrelation in z domain, that is rxx of l. Okay, so this is nothing but the z transform of this autocorrelation sequence, okay, as per this correlation property, right? So rx1 x2 of l in z domain is nothing but x1 of z multiplied by x2 of z inverse. The same thing has been indicated here, right? So to get this Rxx of z, initially we need to determine the z transform of x of n, and then as per time reversal property we can determine x of z inverse, or we can determine x of z inverse from x of z simply by replacing z with z inverse. Right. So uh, initially identify capital X of z from x of n. Okay, so the z transform of x of n is given as, it will be determined, so transform of x of n is nothing but summation n is equals to minus infinity to infinity x of n into z to the power minus n. So this is nothing but your capital X of z. Okay, this capital X of z will be equals to summation, so here x of n is starting with 0, 1, 2, 3. Okay, so at n is equals to 0 value is 1, at n is equals to 1 it is minus 2, at n is equals to 2 it is 4, at n is equals to 3 it is 1. So you can take it as n is equals to 0 to 3. Okay, this summation limits, and you can write here x of n into z to the power minus n. If we are substituting these values, so it will be x of 0 multiplied by z to the power 0 plus x of 1 into z to the power minus 1 plus x of 2 into z to the power minus 2 plus x of 3 into z to the power minus 3. So if I am substituting these values, x of 0, okay, x of 0 is 1, x of 1 is minus 2, x of 2 is 4, right, and x of 3 is 1. Okay, so if I am substituting these values, so I will get x of z. Okay, so x of z will be, the value of x of 0 is 1, so 1 multiplied by z to the power 0 will be 1. Okay, so z to the power 0 is 1, then x of 1 is minus 2, so minus 2 z inverse will be there. Okay. So it will be 1 minus 2 z inverse, right, then plus x of 2 is 4, so 4z to the power minus 2 will be there, so plus 4z to the power minus 2, and then last value is 1, so 1 multiplied by z to the power minus 3, z to the power minus 3. Okay, so this is required x of z, that is 1 minus 2z inverse plus 4z to the power minus 2 plus z to the power minus 3. Okay, so from this x of z, because we want to multiply this x of z with x of z inverse, right, so we can simply replace from x of z to write x of z inverse, so wherever there is z, we'll be replacing it with z inverse. Okay, so it will be simply 1 minus, so 2 z will be replaced with z inverse, so this minus minus plus will be there, so it will be 2z plus 4z square plus z cube will be there, right? So this will be x of z inverse, right? So now if I want to identify the this rxx of z, so for identifying rxx of z, I have to multiply this x of z with x of z inverse. Okay, so x of z is 1 minus 2z inverse plus 4z to the power minus 2 plus z to the power minus 3. So multiplied by 1 minus 2z plus 4z to the power minus 2 plus z cube. So initially I will multiply it with 1. Okay, so it will be 1 minus 2z plus 4z square plus z cube will be there. Okay, then I will multiply it with minus 2z inverse, so it will be minus 2z inverse. Right? Then this minus minus plus will be there, so plus 4 z inverse multiplied by z, so this will be z to the power 0, right? Then minus 8 z, right? 2 minus 1 will be there, z to the power 2 minus 1 will be 1. Then minus 2 z square will be there, right? Similarly, you can identify or multiply it with 4z to the power minus 2. It will be 4z to the power minus 2 minus 8 z inverse, right? Then plus 16, right? Then plus 4z. Okay. Then I will multiply it with z to the power minus 3. So plus z to the power minus 3 minus 2z to the power minus 2 plus 4z inverse plus 1 will be there. Okay. So now I will simply add these values. Okay, so rxx of z will be, so here 1 is there, then 4 is there, right? So 1 plus 4 will be 5, 5 plus 16 will be 21, then 1 is there, right? So it will be 22. Okay, so this 1 plus 4 plus 16 plus 1. Okay, next I will identify it for z, okay, minus 2z. So here it is z, again there is minus 8z, right? So this z minus 2z minus 8z will be minus 10z. So minus 10z plus 4z will be minus 6z, right? So here it will be minus 6z. Okay, so there are only these three terms, that is minus 2z, minus 8z, then minus 4z, sorry, plus 4z. Okay, then z square, for z square there is 4z, okay, 4z square, then minus 2z square, so it will be 2z square, right? Then there is nothing, so plus 2z square will be there. Then for z cube, so z cube is here, then z cube, okay, so there is no other term for z cube, so plus z cube will be there. Then for z inverse, so it is minus 2z inverse, then minus 8z inverse, so it will be minus 10, then 4z inverse. Okay, so plus plus, so it will be minus 6 z inverse will be this, right? Then after that z to the power minus 2 is there, so 4z to the power minus 2, right? Then minus 2z to the power minus 2, so it will be plus 2z to the power minus 2, okay? 4z to the power minus 2 and 2z to the power minus 2. Then the remaining term is plus z to the power minus 3, okay? So I'll rewrite this equation. Rxx of z is equals to, what is that, 22 minus 6z, 22 minus 6z plus 2z square plus 2z square plus z cube plus z cube minus 6z inverse plus 2z to the power minus 2 plus z to the power minus 3. Okay, so I'll just rearrange these terms because I'm interested in identify autocorrelation in time domain. Okay, so I need r small r x of L sequence, right? So I'll just rearrange these terms. So I'll write initially z cube plus 2z square, then minus 6z plus 22, then minus 6z inverse plus 2z to the power minus 2 plus z to the power minus 3. Okay, so we know that in this, at this place, that is 22 is multiplied by z to the power 0, so this will be the origin sample value. Okay, this coefficient will be the origin sample value. Then this will be at n is equals to minus 1, okay, because z to the power minus n is there, so minus minus plus will be there, so it is z. Okay, so this is at n is equals to minus 2, n is equals to minus 3. This will be at n is equals to 1, 2 and 3. Okay, so this is nothing but the required multiplication, okay, and to get the auto correlation sequence, that is Rxx of L, identify inverse Z transform of Rxx of Z. Okay, so we have to only identify the inverse Z transform of Rxx of Z, and that will be indicated as Rxx of L. Okay, and it will be simply the coefficient of this expression. Okay, so at origin value is 22, right? At n is equals to 1, value is minus 6. At n is equals to 2, value is 2. At n is equals to 3, value is 1. Okay, and similarly at n is equals to minus 1, it is minus 6. N is equals to minus 2, it is 2. And n is equals to 3, minus 3, it is 1. Okay, so this is the required autocorrelation sequence for the given sequence x of n. Okay. So again, as we discussed in the previous session, finding convolution by using set transform property is somewhat computationally efficient. In similar manner, finding the correlation by using correlation property of Z transform comprises minimum number of computational operations compared to the identifying correlation by using the mathematical expression, right? So in this correlation property, we are saying the x1 of n and x2 of n has the Z transform x1 of z, x2 of z. Then the correlation of x1 of n and x2 of n so domain will be the multiplication of x1 of z and x2 of z inverse. And we are determine this autocorrelation sequence of x of n signal by using this correlation property of Z transform. Okay, so initially we are determining the Z transform of x of n. So that Z transform is denoted as capital X of Z. From x of z we have determined x of z inverse, and we have multiplied x of z and x of z inverse, right? So we get this autocorrelation sequence in z domain. So we have taken the inverse z transform of it to determine the actual autocorrelation sequence in time domain. Okay, so again similar process is there as we have seen in the previous session. Okay, so to summarize, it involves the three steps. Okay, first we determine the z transform of x1 of n and x2 of n. Okay, so it will be simply x1 of z, so it is nothing but the z transform of x1 of n, and then x2 of z as z transform of x2 of n. Okay, so here again this time domain signal is transferred to z domain. Okay, second step, from x2 of z determine x2 of z inverse, right? In third step, multiply. So here the signal is in z domain, then multiply what is x1 of z and x2 of z inverse. Okay, so to get this multiplication sequence we are indicating as rx1 x2 of z, it will be x1 of z multiplied by x2 of z inverse. Okay, so again it is in z domain, and in fourth step identify the inverse z transform of rx1 x2 of z to get x1 x2 of l. So here the z domain signal is converted back to time domain. Okay. So this is the process of identifying the correlation by using correlation property of z transform. Okay. So in next session we'll be discussing rational z transform. Okay, so thank you for joining this session.